To learn how to use PyNWB and get access to all the resources, I encourage you to go to pynwb.readthedocs.io. Is that visible? From here, you can access all the tutorials and other documentation about the software. For today, we're going to jump into the tutorials and then go to the file basics. Feel free to follow along. I'm going to walk through this page here and add commentary and simplify some of what is described here. Feel free to ask questions as I go. At the bottom here, you can download a Jupyter notebook and the Python file associated with this. Note that if you download the notebook, you won't get the images, but you'll still have all the code there ready for you to execute if you'd like. And I'm going to make this a lot bigger. Similarly, if you work in MATLAB, you go to, you can just Google MatNWB, and that should take you to this page or this page. Both will get you here. That's the README. And from here, if you go down, you'll have instructions of how to download MATLAB, and then we'll walk through the first introduction here together. And I'm going to flip-flop between Python and MATLAB so that we cover the same topic, but in both languages. Okay, so PyNWB and NWB file basics. So in NWB, each experimental session is organized or is represented by a separate NWB file. And so your experiment is typically going to be a collection of NWB files, one per session. Within PyNWB, we have NWB file objects, and these provide some functionality for creating and accessing data of all the different data types that you have. And each data type is typically represented by a different class in Python that handles the requirements of the metadata for that class. The most common ones that you'll see are going to be time series data sets for storing time series data, like voltages over time or fluorescence over time. And then you have processing modules, which are used to organize your process data together into meaningful groups. So time series data, as the name suggests, stores the time series object stores time series data. Within NWB, these objects follow an object-oriented inheritance pattern, if you're familiar with that. So time series serves as the base class for a number of other types, like electrical series or two-photon series, and each of those kind of add on additional fields or modify the requirements for storing that kind of data in some way. But the time series is the base class, and it handles storing your voltage, your measurements over time, as well as the timestamps, as well as kind of like a base description for your data. And you can see many different time series subtypes for extracellular and intracellular electrophysiology, optical physiology, and there's a handful more. And processing modules are used to organize, group all these data types together, kind of like having folders in your file system. And we have different ones designed for different analysis to kind of tag a data type for that analysis or for that kind of data. So we'll have one of the most common ones is position for storing spatial data, like the position of your animal, and LFP for storing voltage traces over time and saying that those are LFP data as opposed to other types of data. At its core, you saw in the earlier talks today, NWB employs a hierarchical organization of data under the hood. And you get exposed to that a bit when you're asked basically to select where in the file to put certain kinds of data. there's a group within the NWB file called acquisition. This is meant to store any raw acquired data that should never change throughout the course of your analysis. And then you have a group called processing for process data, typically the results of your spike sorting, ROI detection algorithms, your pose estimation and video tracking data, and so forth. We also have a group in the NWB file for analysis. You're storing the results of your data analysis, and it's for stimuli, any images that you presented to the animal, videos, and electrical stimulation as well. Okay, now to start on the Python side in PyNWB, we're going to import a whole bunch of things, and you can just copy these. These classes are located in various modules within the PyNWB package, depending on what category they're in. But you can just use this as a reference. And we're going to start by creating a base NWB file. Now, again, an NWB file represents a single session for an experiment, and there's a few required fields. A session description, like what happened during the session, an identifier field that we usually ask you to use a universally unique identifier, or UUID for that, and a session start time that is used as the reference point for all of your timestamps in the data. So if you have a timestamp of 0, that means that data point occurred at the session start time. So we're going to use PyNWB. We're going to create an NWB file object using with these required fields and additional metadata that you might want to provide to, you might want to include. So you do that by calling the constructor and then passing all of these as arguments: session description, identifier, session start time, and then you can add additional metadata saying who was the experimenter, what lab and institution is this data collected from, any publications that you want to link to your data set, and so forth. And you can click on NWB file here to get the full documentation of the constructor. And you can see all the many different fields that you could add about keywords, about the virus, the protocol, the source script of what file you use to generate this data, and so on. Once you've created that object, you have a basic empty NWB file. And if you just print it out, here in a Jupyter notebook, you get this nice representation that you can kind of click through and browse. Okay, so next we're going to create or add subject information to our NWB file. We can store information such as the subject's age, species, genotype, sex, and a description. For all of these are free-form text fields, but we have recommendations that you follow particular conventions, and that helps any software tools like the Dandy Archive interpret the data and enable people to search for all data sets from that are collected in mice. So we ask that if you enter the age, that you use a particular ISO 8601 duration format that basically says it starts with a P, it's a number of, in this case, days, 90D for days, or 90D12H for 90 days and 12 hours or so. And you can click that for more. For species, we ask that you use the formal Latin binomial name for your species: Mus musculus, Homo sapiens, Drosophila, melanogaster. And for sex, I think Dandy actually requires this, that you use one of these 4 one-letter codes for the sex of the animal. And to add this information to an NWB file, it's pretty easy. You just create a subject object, call it the constructor, and pass in all of these fields, just as text strings. And then you say NWB file.subject equals your new object. And you have an object, a subject, and it has been linked to the NWB file. Okay, at this point, I think, let's see. I'll go a little further and then switch to MATLAB briefly. Okay. Next, I'll cover time series data. Time series is the common base class that we use for all measurements sampled over time, and it has a few required fields to be time series data. You have a data array, and then you have a timestamps array. The timestamps can be regularly or irregularly sampled, meaning so if you want to store all of your timestamps explicitly, or your timestamps are not, does not have a regular sampling rate, then you pass an array of timestamps. But if you know your data is sampled at 30,000 hertz and it doesn't change from that, there's no dropped frames or anything, then you can just store the rate and the starting time, and that will save you a significant amount of space in your file. To create one of these objects, it's as simple as the other ones. You call it the time series constructor, and you pass in all the fields. In this case, we're passing in a list with of integers from 100 to 200 as the data. You specify your units. In this case, is m for meters, and in this case, we're using a starting time of 0 and a rate of 1 hertz. Now, for your data, if you're storing electrical voltage data, it'll be an electrical series object, which has these requirements plus a little bit more for your electrodes information. If you're storing 2 photon series objects, it'll be this information plus a little more for your ROIs. But this is kind of the base structure and can be used for arbitrary time series. If you are working with irregularly sampled recordings, then you pass a timestamps array instead of a starting time and a rate. These actually print out. Okay, so you have an object, but it's not part of the NWB file yet. You have to decide, is it acquisition data, is it process data, is it stimulus data? And you can call these functions here on the NWB file to put it into the file. NWB file.add acquisition, and you pass in your time series object. To retrieve the data, the time series object that you put in, call get acquisition and give it the name, and you can get it back out. Okay, so now we're going to take a very brief detour to jump into the MATLAB version of this. For MATLAB, for MatNWB, you have to install MatNWB according to these directions, and it's pretty similar to the Python code. We have an NWB file class here that you pass in all of your arguments for your metadata fields as kind of key, comma, or key value pairs to the constructor. And so you can add in the session description, identifier, and session start time. Those are required, and then the rest of these are optional. The names of the fields can be a little bit different in MATLAB than in Python, so be careful about that and consult the documentation. And if you print it out, you can see all the different metadata fields, including all the ones that are empty that you did not fill in. Similarly, for a subject, the subject object is in types.core, and so you call it types.core.subject, and you pass in your key value pairs to create a subject object, and then in this case, it's nwb.general_subject equals subject, and that way your subject is part of the NWB file. Okay. All right, so those are the basics of writing your subject information, kind of generic time series data, which serves as the basis for all the other kinds of subclasses of time series data, and creating the file. So now let's start adding some behavioral data. Let's say you have a freely moving animal as part of your experiment, and you want to store their XY position over time. For this, we have a data type, a neurodata type called spatial series. It's a subclass of time series. You can see it represented in this little class relationship diagram here. The spatial series says that the data field of the time series is restricted to be a two-dimensional array of time by features, where features is 2 for XY or 3 for XYZ data, and the unit is fixed to meters. We want to standardize how the data are stored to make it easier for tool builders and other folks who are reading the data to know what what the data represents. In addition, we have another field. The spatial series adds another field to time series, and that field is called reference frame, and that says, where is the 0, points in your, what is the value of 0 represents in the real world for your data. And that's just a free-form text field for you to describe, like, is it the center of your maze, or is it like the somewhere off screen or off world? To create a spatial series object, it's very similar to the other types. You call the constructor and you pass in as keyword arguments the name, the values for all of these fields. Name equals spatial series. Pass a description. You pass in your data. Oops. I did not realize that would link. And here we're just using fake data. It has a shape of 50,2. Importantly, what I didn't mention before is that in time series data and all of its subclasses, the first dimension should always be time. If it's not time, that will confuse any tools that assume that it's time. And we check for that in the inspector as well. But just remember that, the first dimension is time. The second dimension in the spatial series case is the XY position. The timestamps is another array. It should be the same length as the first dimension of your data array. And then here we have a reference frame saying that 0 is in the bottom left corner of the maze. You create the spatial series object. You can print it out. You can see the fields here, including the ones that you didn't set. But it's not part of the file yet. Now, and it doesn't exactly represent the position of the animal necessarily. The spatial series is generic as representing XY of something. Now, to help analysis and visualization tools know that this spatial series object represents the position of the subject specifically, you store the spatial series object inside of a position object. And this position object is kind of like a container or a box that can hold spatial series objects. So create a new position object. You can name it position. By default, it's named position. And you just pass it in as an argument. And so you have a position object there. Okay, and then we still need to add it to the file. To do that, we want to put it into a processing module or a folder called behavior, which organizes all of the behavioral data related to this subject. And there are various processing module names that we recommend for different types of behavior or different types of data. So if your processing module is called behavior, if you're working with behavioral data, put all those into a behavior processing module. And similarly for ECEFIS, that goes in an ECEFIS processing module. And creating one of these is pretty straightforward. Call NWB file.create processing module, give it a name, give it a description, and then you can call the .add function to put stuff into it. And because this processing module is already part of the NWB file, so this effectively adds your position data to the file. You can access that data then by calling NWB file.processing and put in square brackets the name of your object, the name of the processing module, and you will get this. This is a processing module. It has data interfaces within it. One is the position data, and that has spatial series data, and there's your data and timestamps for your XY positions. Okay, so now your spatial data is part of the file. Let's write it to disk, and so that it's not just in memory. To do that, we use the NWB HDF5 IO class. I know that that's a mouthful to say, but NWB first. HDF5 is a common storage system for large-scale scientific data, and then IO for input-output. So to write an NWB file, you initialize this IO object, you pass in a file name, you say mode equals W for write, you would change this to R for read, and you get an IO object, and you just call io.write the NWB file, and then you close it at the end. You can also use it in this way, a more kind of Pythonic way, with the with context manager, and that way it auto closes at the end of the execution. Okay. Now to read the file, we use a very similar function called with NWB HDF5 IO, pass the file name, mode is R, and then you call io.read, and you get back an NWB file object. And you can access different elements of this NWB file in this way, calling acquisition, square brackets, whatever the name of your objects are, or dot processing, square brackets, the name of your behavioral module, and so forth. Now, importantly, when you read the data back in, the data arrays, your data array, your timestamps array, anything that is like big and bulky, that was a list or a NumPy array, all of these are read passively from the file or lazily from the file. So if your data is a terabyte, opening the file will not crash your computer. Instead, NWB or PyNWB provides this interface that allows you to kind of query the metadata around the data set, the data array, and if you and then you can slice into it to access particular segments of your large data array. You can use the square brackets colon operator here to read the entire array into memory, or you can slice it in typical NumPy fashion to say you want the first two rows or like a particular segment in the middle. Okay, and I kind of talked about it before, but you can access particular objects or data types within your NWB file by traversing the tree and saying NWB file dot processing, pass it the name of your processing module, and within there is your position object. You can print out the objects so you can know what to enter next. And eventually you'll get down to the spatial series object that has your XY over time. Okay, now on the MATLAB side, it's very similar. The names of the classes are all the same, but how you store it is just slightly different. Because MATLAB indices stores matrices in a bit of a reverse order as Python, in MatNWB, timestamps, time is always the last dimension of the arrays. And it will be mapped appropriately so that when you read in Python, it's read as the first axis, and when you read in MATLAB, it's the last axis. But this is just differences in the two languages. So when creating this object in MATLAB, you call the spatial series object to represent your position data. Call it types.core.spatialSeries, pass in data, reference frame, and timestamps as key value pairs, just like for all the other keyword arguments. And then you can create a position object, put your spatial series in it, create a processing module for behavior, and put that into that. And then add your add your position data to that processing module. And then that processing module needs to be added to the file by calling nwb.processing.setBehavior to the behavior mod. The syntax is slightly different between Python and MATLAB, but you can follow the tutorial here to see how it works. Okay, so we finished with subject information and general metadata, finished with basic behavioral XY positions over time. I'm going to skip this briefly here, and then we'll jump into trials. Many of you are working with animals who are doing some task and that's repeated over time, or trials. And we store that within NWB using a time intervals object, which is a subclass of dynamic table. Dynamic table is a type that holds that is used to store tabular metadata throughout the NWB standard, and this includes trial data, includes electrodes data or ROI data, includes your sorted data from your sorted spike sorted units, and these tables they define that you have particular columns with particular data types within those columns, and they also allow you to add additional custom columns that are not defined in the standard, because oftentimes we find that you as an experimenter, your trials are going to be different than someone else's trials, and so we can't form a common standard around every possible metadata that you might want to add. So we allow you to just add any additional columns as needed. The trials class can be thought of a table in this structure. The columns are their own data sets, and you just have to have the same number of rows across each of them. So the first trial here might have a start time and a stop time, 1.1 and 1.5, and then you can add additional columns as needed. By default, all of these time intervals objects, like trials, they must have a start time and a stop time. You can call add trial column to add these additional columns. But once you add them, they become required for every trial subsequently that you create. So here's an example, NWB file.add trial column, give it a name, correct, and it represents whether that trial, the animal got that trial correct. Then you can call NWB file.add trial, pass in start time, stop time, and correct equals true or false, or this could be an int or a float, depending on what it represents. And you can put that in a for loop to go through and add all the trials to your NWB file. For convenient analysis and visualization, you can convert these tables to pandas data frames using the .toDataFrame method, and then you get a more traditional tabular representation like this. Some of you might not be working with trials, but instead epochs or intervals of time that represents like the animal is sleeping or the animal is running. You can use similar methods. Instead of add trial column, it would be add epoch column. Instead of add trial, it would be add epoch. And it works in pretty much the same ways. The only slight difference is that you have the option of linking these epochs to particular time series to segment those from those epochs out of your time series. Again, you can call it toDataFrame to get those in a pandas data frame representation. And you can also create time intervals objects that are not trials and not epochs, and add those to the NWB file as well. Finally, you can call NWB HDF5IO again, but because all of these objects are currently in the in-memory NWB file, they haven't been written to disk yet, except for what we wrote initially. We can write them all again to disk, and by calling io.write. And the W will overwrite anything that was previously written at this path, and that, that'll be fine. If you want to instead append to an existing one, an existing NWB file, you change the mode on this NWB HDF5 IO object, to A for append. Then you read in the data, you create any new objects that you want to add to the file, like this time series, and you call add acquisition or add processing or processing module.add x, and the new object will be added to the file. Then you call io.write, and then it will be added to the file. Importantly, this works for appending or adding new data to a file. Removing data from a file is significantly trickier and not as well supported due to the HDF5 file format. You can remove things, but it won't actually shrink the file. In MATLAB, it works very similarly. Trials are stored as dynamic table objects, as I mentioned before, but because they are time intervals objects at their base, and you have to provide a few more metadata fields that the Python API covers automatically, and this allows you to write in the start time and stop time and any names of columns, and then you pass in the values of each column individually, and then you set it onto the NWB file using nwb.intervals_trials equals trials. With MATLAB, if you are writing the NWB file, all you do is call NWB export your object and the name of the file, and you're done. You have a file. You can call NWB read then to read it back in, and just like in Python, these data files or data objects, data arrays are read lazily, and so you don't overwhelm your computer by opening a 1 terabyte file. Just like in Python, we can traverse the NWB file hierarchy to get to particular data objects. So here, your NWB file has a processing module called behavior, and that has a object called position, and that has a spatial series called spatial series, and then you get to your spatial series object, which has your XY positions over time. And then this is demonstrating the data reading capabilities. The data are not read by default, but if you call data.load, it will load it all into RAM, or you can slice the data using this syntax here. Read spatial series.data, and you pass a slice for each axis. Okay, so that was probably a lot to take in, but that covers the storage of general experimental metadata and subject metadata within an NWB file, how to store spatial series data and position data, and more broadly, behavioral process data in the NWB file, and how for you to add trial information. One limitation of the NeuroConv software that Cody demonstrated earlier is that trials are not added because they're not part of your proprietary acquisition file format. You still have to go in and add any trials to the file yourself. And yep. Exactly. Yeah. So open the file in append mode, and then call NWB file.trials or add trial, passing in any information about your trials, and add custom columns as needed, and then call io.write to add them to the file. Yeah, and that's it for this first talk and tutorial. Do you have any questions about kind of the basics of NWB? And then we'll go into more domain-specific or data type-specific instruction in the next couple talks.